We recap the things that we discussed last time. So last time we discussed the some of the limitations of the NeRF pipeline. So we discussed the basically long computation time. So we also so that some kind of the hybrid representation basically can handle this kind of the computation the time issues in the NeRF pipeline. And the other limitation kind of the NeRF was that basically it requires the many kind of the images from the multiple reviews. And the question is that can you also basically get some kind of 3D the outputs with some very sparse the number of the images. And the dream field is one of the kind of the example that was like going to the extreme the case, which was basically the case that even without like having any images, even from a kind of the text prompt, can you still do some kind of the 3D generation? So now we are just going into some kind of the case that we are not reconstructing 3D, but also we are generating the 3D from any other kind of the images or any kind of the inputs. But the only input is basically the text prompt. So how can you do this kind of 3D generation using some kind of the image prior was basically the things that we were discussing last time. And then the next question was that, can you also use some kind of the other types of the image priors, not only the clip, but also some kind of the image generated models as well. And then we started to discuss that the diffusion model is basically some kind of the recent model that is giving this some kind of the best performance in terms of like giving the very high quality of the generated images. Then the question was that basically, can you somehow utilize this kind of the image, the generative models in terms of like creating some kind of the 3D the outputs? So for that, we started to discuss some kind of the basics of the diffusion the models. And the very high level the idea for the generative model is basically learning some kind of the data distribution. So this was basically the one example in terms of that we are having some kind of the distribution that is basically indicating how likely the data points for each of the point in the given the space will be some kind of the realistic kind of the data point. So it can be image or the text or whatever kind of things. It can be audio, video, any kind of things. So we can basically say that all the data that we are basically dealing with this is basically living in some kind of a certain space as kind of the one single point in the space. We are basically having some of the samples of some kind of the realistic data or some realistic images or realistic audios, whatever kind of things. And given these kind of samples, like can you somehow recover the whole the distribution that is basically indicating how likely each of the data point in the space is kind of the one of the realistic data. And the idea for that is that given this kind of samples, actually we want to basically transform the given the data distribution in a way that it basically becomes some kind of the much simpler kind of distribution like the unique Gaussian distribution. Especially for the case that the target distribution is the unique Gaussian. Sorry, my mic please. Yeah, is the sound okay now? Yeah, so when the target distribution is basically the unique Gaussian, the way that we are making this kind of the transformation is basically simply just like perturbing each of the data points, basically adding some kind of a small Gaussian noise in a way that for each of the points in the given space, we are basically sampling some small noise in a way that we are moving that point into some kind of the neighbor point. And the interesting is that if we repeat this process multiple times, then the given the data distribution will be basically converted into the unique Gaussian. So that's basically the things that we are going to see, like why it happens in some kind of the some formulations. Actually, the thing is that the reason why we want to do this is that actually we want to learn the opposite. So actually, if we can also convert the given the unique Gaussian distribution into the data distribution, then what we can do is that we can basically sample from the data distribution in a kind of like indirect way, in a way that we are basically sampling from the unique Gaussian the distribution, and then basically mapping that point into one of the point in the data distribution. So basically, we are sampling from the unique Gaussian, and we are just basically mapping that all the way back to the data distribution in a way that the output becomes the one of the data point from the data distribution. So that's the very basic idea for the most of the generative models, not only for the diffusion models. Basically the things that is basically added to the diffusion model is basically this kind of some iterative process. So this mapping from the data distribution to the target distribution is not the kind of the one step the mapping, but it's kind of some sequential the mapping. So that's basically what we are going to see, how we can make this kind of some sequential mapping from the data distribution to the target distribution, and how we can also learn the reverse function mapping from the target distribution to the data distribution. So that's basically what we are going to do. And this was basically one of the 2D examples that we are starting from the data distribution, which is basically starting from the Swiss roll kind of shape, and then gradually mapping this into the unique Gaussian like this. And now we are also mapping the other way around. From the unique Gaussian, we are also getting back to the original the data distribution like this. So from, this mapping, mapping from the data distribution to the target distribution, once we get this, if we can go the opposite, like starting from the unique Gaussian to the data distribution like this, then what we can do is that basically we can, even without having some explicit representation for the data distribution, we can basically sample from the unique Gaussian and just map this point to the one of the data point in the data distribution. So that's basically what we are going to do. And this was kind of some comparison with some other kind of general models as well. So let's get into slightly more some details about the basic idea for the data distribution. Especially we are going to discuss this specific model, which is the DDPM, denoising diffusion probabilistic models. And we're going to also discuss some other things in the next time. So basically for the process, mapping from the data distribution to the target distribution is basically defined like this. So we are having the QX0, which is the data distribution here. Down here. And then we are going to map this into the target distribution in the PXT. And also here, one key thing is that we are basically not learning this kind of the mapping, but this is kind of the fixed the procedure. Basically, these are all the kind of things that the user is basically defining. Sorry, my iPad is not. So it's basically the fixed procedure, which is defined as kind of the Markov chain, which is basically the case that the data point at the time t is basically defined based on the data point in the previous time. So we don't need to have any kind of memory from the previous time steps. If we have the data point at the time step t minus 1, based on that, we can basically determine the next position of the data point with this kind of the Gaussian, the transition, the probability density function. So which is basically showing that like when you have some kind of the xt minus 1, how likely the data point here at the xt minus 1 will be basically moving to the xt at the time step t. So this is basically what we are going to do. So, and as you can see, this is basically defined as kind of the Gaussian. So this is basically the things that we are adding some kind of the small the Gaussian noise in a way that we can perturb each of the data point at the time step t minus 1 to the some kind of the near the points. And we are defining the Gaussian like this. In this way, you can see that, and also all these kind of the parameters, the beta, is basically some kind of the user parameters. And we are going to slowly increase this kind of beta over time, but still all the beta would be very small in terms of that. So as you can see, if the beta is basically close to 0, if the beta is basically 0, then you can see that this becomes the just the unique Gaussian, right? So if the beta is basically 0, then this the Gaussian will be just no, it's not unique Gaussian. It becomes basically this. So basically, the variance basically becomes 0, and basically this will be some kind of the Dirac delta function in a way that the data point is not moved, right? So if you were basically at the t minus 1, if the beta is 0, then you are not moving the points. You are basically staying at the same point. But as you slowly like increase the beta, you can see that we are also slowly increasing the variance here, and also moving the point to slowly get closer to the origin, right? So if I just do this, as the beta is basically getting the larger than the 0, then we can see that the mean of this Gaussian becomes getting closer to the origin, and also we are adding some kind of a small noise in the variance. So you can see that as we basically increase the beta and also repeat the same process, it's basically slowly like moving each of the points to the origin of the space, while basically adding some kind of the noise with some kind of the perturbation in the variance here. And we are basically stacking all this kind of this Gaussian transition in a way that we are making the transformation from the data distribution to the target distribution. So that's could be basically the fourth pass. Basically we are basically adding some kind of the Gaussian noise. And obviously, this is kind of like the one way that we are defining some kind of the fourth transition. And there are many other ways of like defining this kind of the fourth transition. So this way is basically like they call the case of like variance the preserving the form. And there's some other kind of forms of the like making some kind of the defining the fourth transition. We're gonna stick to this specific case. Basically define the fourth transition in this way. Any questions? What is the I in the variance part again? Yeah, the question is that what is this? This is nothing but basically the identity, the matrix. So everything is here might be basically the multivariate, the multidimensional, the variable, right? So this will be basically nothing but just the identity matrix. So that's basically the things. This is the 4D process. And the reverse process is also defined as kind of the Markov chain as well. So here actually the thing is that our goal is that we are defining the 4D process in a way that the other way around from the target distribution to the data distribution is also defined with as kind of the Markov chain with some kind of the Gaussian transition as well. But at this point, the thing is that while we are having the transition of the 4D process, this is kind of the given, right? So we are fixing the fourth transition with some kind of the specific parameters would be better. But based on that, actually, we need to actually predict the opposite, the reverse the transition from the xt to the xt minus 1. So basically, the thing is that what we are going to do in this diffusion model is that when you basically define the fourth process in this specific way, how can you also discover the reverse process, which is basically mapping from the target distribution into the data distribution? And also, we want that this reverse process is also defined as kind of the Markov chain with the Gaussian transition in a way that all the computation becomes divisible. So that's basically what we are going to do. So also in the same way, the reverse process is basically defined as like we are starting from the target distribution and basically repeating this kind of the reverse the transition multiple times, which is defined as the Gaussian transition in a way that the output also basically matches the given the data distribution. The target, sorry, not target, the data distribution that we want to basically learn. So that's basically what we are going to do. Make sense? Then once we can get basically this kind of some kind of the learned the data distribution, what we can do is that we can basically check whether the learned the data distribution is basically good or bad in a way that when you have some multiple samples from the given the data distribution, we can check whether the probability, the density value given the distribution for each of the samples is basically high enough or not. So we are basically maximizing the probability density values for the given samples based on basically the learned the data distribution, which is defined as kind of some iterative transition from the target distribution. So that's basically what we are going to do. So we are having some multiple samples from the data distribution. From these samples, once we get this kind of the whole deformulation, like basically, representing the data distribution as kind of this kind of transition, we are maximizing all the parameters in a way that we are basically we are maximizing the loss function in a way that we can represent the data distribution as kind of this kind of transition. So here basically what we can see is that this is kind of the unknown information. So here the thing is that how we can learn this kind of the reverse the transition every time step in T. And basically this the reverse the process, each of the transition in the reverse process will be basically learned using the neural net. So you can see that this basically theta is basically representing the parameters of the neural net, and then basically every the Gaussian the transition in the reverse process will be basically predict using the neural net. So we are basically optimizing all the neural net parameters in a way that once you get the data distribution like this, the probability, the density values for each of the data point becomes basically maximized. So that's basically what we are going to do. Any questions on this? So also the important thing in terms of like understanding diffusion model is that we want to basically make both the forward process and the reverse process as kind of some sort of the iterative, the Gaussian, the transition, the steps. So for each of the time step, both the forward process and the reverse process, each of the transition is defined as kind of the Gaussian the distribution. And also the thing is that we are basically defining the forward the transition in this form, right? So if I just go back to the previous slide. Yeah, so we are defining the forward the transition in this form. But the thing is that when we define any kind of a arbitrary default transition, it does not guarantee that the reverse transition also becomes a Gaussian. So the thing is that when we only basically make the forward process as kind of the Gaussian distribution with the small beta here, with some basically small d variance here, then it becomes like easier to basically approximate the reverse process as kind of the Gaussian as well. So that's kind of the key thing. So if you actually want to make the reverse transition can be approximated as another the Gaussian distribution, then we need to actually make this the beta to be small. As we increase the beta to be large, actually, if we approximate the reverse the transition as the Gaussian, that becomes the bad approximation, which means that the reverse the transition may not form the distribution of the Gaussian. So that's kind of the key part. So we want to basically make both of the forward process and the reverse process as kind of the a sequence of the Gaussian the transition. And in order to basically approximate the reverse transition as kind of the Gaussian, we need to make this beta to be small. So that's basically what we are going to do. So we're gonna get back to this point later. So that's kind of the key part. So this is kind of one of the examples that when you train the diffusion models with the 2D images, what sort of the images we're gonna see. So as I also mentioned in the previous time, now we are representing, considering each of the image as kind of a single point in a very high dimensional space. So when you basically have some images with the 128 times like 128 the resolution with the 3 color channels, then we can consider that each of the data point, each of the image is kind of a single point in this high dimensional the space, right? Or we can first map all the images into the latent space and consider the images as kind of one of the point in the latent space. So we are starting from the like one single point in this kind of very high dimensional space. And we are basically adding some kind of the small noise in terms of like, moving the point in the other point in the high dimensional space. And so we are getting like, this kind of the sequence of the images every time when you perk up the kind of the noise. And then we are getting some kind of a sample of the unique Gaussian. And then we are going back to the original the image in terms of like running the reverse process. So that's basically what we are going to do. Is this clear? Any questions on this? So then now we have the two main questions. The first question is that, so when you repeat this kind of the full process, can you really see the results that the distribution is really converging to the unique Gaussian? So we are basically adding some small the Gaussian noise for each of the data points, and does it really converge to the unique Gaussian? So that's the first question, right? And the second question might be is that like, so basically when you have this kind of the given the procedure of the full the transition, how we can also predict the reverse the transition that can also recover the data distribution from the unique Gaussian. So these are the two main questions, right? So let's get into the first question. Yeah, so this is the first question. Does the full process really converge to the unique Gaussian? And the answer is obviously yes. So let's see how we can really see that the results that the full process is like converging to the unique Gaussian. So this is basically the fold transition that we defined. As I also said, there are some multiple other ways that like making the fold transition. But basically here the idea is that we are basically adding some kind of the small Gaussian noise into this given the data point. So that's what we are going to do. Let me briefly basically rewrite this 1 minus the beta t as kind of the alpha t, just to make the derivation easier. Yeah, we're gonna basically have this form. So now we are having the alpha instead of the beta, basically the same thing. So you can see that. So I recommend you to basically write down those things yourself and see whether it really makes sense. So we are having this kind of the one-step transition, which is defined as kind of this specific the Gaussian distribution. And what we are going to see is that can we derive this kind of the jump from the x0 to the xt, this kind of the posterior distribution by it's kind of the sequence of this kind of the one-step transition. So from this kind of the sequence of the one-step the transition, how can you derive this kind of the jump from the x0 to the xt? So that's basically what we are going to see. For that, like one simple basically effect that we need to basically see is that we can basically easily represent a sum of the two the samples of the different kind of the Gaussian as kind of the one sample from the some kind of the convolution of the two Gaussians. So let's think about this case that we are having the one sample from this Gaussian distribution and the other sample which is also coming from this Gaussian distribution. Then if we take the sum of these two, then actually this can be considered as kind of the one of the sample of this combined the convolution. So that's basically one simple the fact that we're gonna basically utilize. Makes sense? So if we have like one sample from the Gaussian and the other sample from the other the Gaussian, the sum of these two is also follows the convolution of these two Gaussian. So basically, the sum of these two can be also considered as kind of like one of the sample of the one unified the Gaussian like this. So that's basically the simple fact that we are going to utilize here. And based on that, let's basically see the long kind of derivation here, which looks a little bit like the complicated. But let's basically get into the details like line by line. So what we are basically seeing is that here, so what we can see is that, so we are basically, we know that each of the xt is basically a sample of this Gaussian distribution, right? So we can basically also rewrite the xt as kind of like this form. This is basically representing as kind of like each of the sample as kind of the mean plus some kind of the scaled the Gaussian noise, the noise from the unit the Gaussian, right? So you can see that this is basically represented as kind of the mean plus like some the variance times some kind of the noise, which is basically the noise coming from the unit Gaussian. So now we can also represent each of the sample xt as kind of in this form, right? Based on the Gaussian distribution, defining the xt. And then we can also rewrite the xt minus 1 as well in the same way. So it's nothing but basically rewriting the xt minus 1 as kind of also the sample, which is basically so represented as the mean plus like various times the unit Gaussian denoise. Another the unit Gaussian denoise, right? Just rewriting this way. And then now what we can see is that now we are having the two the Gaussian samples. One is basically this epsilon t minus 2 and this epsilon t minus 1, right? These are like two different the Gaussian samples, which variance is basically scaled in this way, right? So now we can combine these two, as we have seen in the previous slide. If we combine these two, then we can basically represent the sum of these two as kind of the like one the sample from the the unit Gaussian with this kind of scale of the variance, right? So this is basically coming from the previous slide. So what we can do is that we can repeat this process until this t minus 2 goes down to 0. So if we basically do this kind of the replacement, like all the variables, then what we can see is that now the xt can be written as kind of the some kind of this form, like having some kind of the scaled the x0 here, and also some plus some kind of a scaled the unique Gaussian the noise. So this is another basically the unique Gaussian the noise, the sample from the unique Gaussian. So from this, what we can see is that now the xt actually can be represented as kind of the sample of like this Gaussian distribution, right? In the previous slide, in this form, now this should be basically the mean, and this should be basically representing the standard deviation. Then based on these two, what you can say is that the xt can be now represented as kind of the Gaussian distribution conditioned by not the xt minus 1, but the x0. And this form can be now written as kind of this Gaussian distribution. Make sense? And alpha t hat is basically defined as kind of the product of all the alpha I. And the alpha basically t was also defined based on the beta t. So this is kind of like a good thing. While basically we are representing this kind of the forward process as kind of the sequential the transition using the Gaussian, actually we can represent any kind of data point at the arbitrary time step t as kind of the some perturbed data point directly from the x0 here. So we can basically see the jump from the x0 to the x0 to the xt as kind of which is also modeled as kind of another the Gaussian the distribution. So that's kind of the interesting effect. While basically we are defining each of the xt, the type with some time step t, as kind of sequential the process of like adding some kind of the Gaussian the noise. Actually, each of the time step, the data point at the time step t can be represented as kind of the Gaussian distribution directly from the x0 here. So this is kind of the one key fact that we are going to utilize in many other places. It is clear? So given the x, the 0, actually any kind of the xt and the arbitrary times the t actually can be directly sampled from the Gaussian the distribution without having the sequential the Markov the chain the process. And that the transition from the x0 to the xt is defined in this Gaussian form. So that's also kind of important effect that we're gonna see. Then based on this, what we are going to see is that, so given this, we also basically want to see whether the xt, basically this form, is finally converging to the unique Gaussian, right? So once we basically start from the x0, like if we repeat this process like multiple times until the time step capital T, whether this is really converging to the unique Gaussian or not, it's kind of the problem that we are going to see, right? And actually the thing is that from this formulation, we can see that this is basically converging to the unique Gaussian when the alpha t hat, this also is becoming 0, right? So if, as you can see here, if the alpha t becomes 0, here, if this becomes 0, then this will be 0, and this will be basically the identity matrix, right? Then this becomes the unique Gaussian. So then the question is that whether this really is converging to the 0. So the thing is that, as I also mentioned in the previous slide, we are making each of the beta to be small enough in a way that each of the reverse the process, the transition also is defined as kind of the Gaussian the distribution. So that's the thing. While we are basically having the multiple beta, we are going to make all the beta to be small enough in a way that we can model the reverse transition as the Gaussian. But the thing is that, so which means that the alpha t is basically defined as kind of the product of the 1 minus beta t. So as the beta t is small, this will be close to 1. But it's still not exactly 1 because the beta is still greater than 0, which means that this will be some number which is like less than 1. And as we basically repeating, multiplying this value over time with some kind of the large time step t, you can see that this product of this part is going down to 0 as we basically go over some more and more the time step. So which means that while when the beta t is like this small, if it's still basically some number which is greater than the 0, then basically this r bar t will converge to the 0 as the time step t is basically going to the infinity. So which means that practically, as we basically have increased the time step to basically some kind of the lots of kind of the number, then you can see that the jump from the xt to the xt, x0 to the xt is converting to the unique Gaussian. So that's basically the things that we can see. So what we can see is that from the given this kind of procedure that we are defining for the process, we can see that at the end of all the sequence of the process, we're gonna see the results that the given the data samples are basically become the sample of the unique Gaussian after like many time step t. So this is basically the answer for the first question. Any questions on this? What does the epsilon t minus 2 bar and the epsilon 0 bar indicate in the previous slide? Okay, so the question is that here, what does this and this and this mean, right? So these are also basically all some kind of the samples of the unique Gaussian, but just different samples. So we're having the one sample, which is sampled at the time step t minus 1. And also the unique Gaussian, the sample, which is sampled at the time step t minus 2. And then now we are representing the sum of these two as kind of the one single the sample from the unique Gaussian. So we are basically now representing the new variable, adding these two as kind of the epsilon the t minus 2 bar. Just defining some kind of new variables, like adding these two. Does this answer your question? Why should the betas be increasing? It seems that it doesn't have to be any. Yeah. So yeah, there are also some kind of the lots of kind of the discussion, like how are we gonna make some kind of the define the sequence of the beta. So so there is also some kind of some discussion in terms of like how are we gonna define the sequence of the beta. We're gonna get into that point maybe in the next time. But yeah, so here basically the point is that we are making the beta to be small enough in a way that we are defining the reverse the transition as the Gaussian as well. But also there are some kind of practically, depending on how we define the sequence of the beta, we can slightly get the different performance in the generation. We're gonna get into that point maybe next time. Any other questions? Okay. Great. So yeah, that's kind of thing. Then sorry, one more question. This square root is a coefficient we choose on our discretization. The question is that the square root of the 1 minus alpha t times alpha t minus 1 is our choice. Well, so the only thing we are choosing is basically this design of the Fourier transition. So we designed the Fourier transition in this way. As I said, there are some other ways to like defining this Fourier transition. But let's stick to this specific design because like this gives the best performance. So when practically, and the thing is that we are basically getting. So this is basically coming from the way that we are defining the Fourier transition, right? So, from this, basically, we are getting this kind of coefficients, and this is basically computed as kind of the combination of like these two the Gaussian samples. Does it make sense? So we can see that basically E t minus 1 can be considered as kind of the Gaussian sample from the 1 minus alpha t. This Gaussian distribution, and also epsilon t minus 2 can be considered as kind of another the samples from the alpha t 1 minus alpha t minus 1. These Gaussian samples, right? So given these two samples from the different Gaussian distribution, how we can basically represent the sum of these two, not this one, basically this one can be sample of this, and this one can be seen as the sample of this, right? If I just like write down as kind of the y t minus 1, like y t minus 2, this can be y t minus 1 and the y t minus 2, right? Then y t minus 1 plus y t minus 2 can be seen as kind of the another the Gaussian sample, as we have seen in this previous slide. So if we have like the samples of the Gaussian distribution, the sum of these two can be also considered as kind of the sample from the this specific the Gaussian distribution. In this way, basically, we can rewrite the summation of like these two as kind of like one the Gaussian distribution. And here, basically, we can see that this is the kind of the unique Gaussian the sample, and this is basically the scale term for the variance. So that's basically thing. We are converting, rewriting all the things. Does it make sense? Any other questions on this? So yeah, so we are basically getting the results in terms of, so there are basically two key facts. So the important fact is that even when the beta is basically small, if we basically repeat this process, the full transition like multiple times with the large time step t, then we can see that the output of the all the transition is converging to the unique Gaussian. So that's also the important fact. And also the other important fact is that like even when we only define the even only when we define this in this specific form, from this kind of a single the transition, actually we can also see that the jump from the x0 to the xt, x0 to the xt can be also defined as kind of the another the Gaussian distribution in this way. So in this full the process, actually we don't need to repeat this kind of transition. We can directly basically sample the xt from the x0 without any kind of the iterative process. But the thing is that while we can basically do this kind of the jump, each of the times the t is actually defined from this kind of the sequential the transition the process. So that's basically what we need to see. It is clear? While we are defining the full process kind of the sequence of the transition, if we want to sample any arbitrary data point from the time step t, then we can directly sample this from the x0 to the xt. So this is kind of the important effect. And then let's move on to the reverse process. So the thing is that what we know is that when the beta t is small, then this will be basically can be approximated as kind of the Gaussian distribution. But still, we don't know what exact the Gaussian distribution is, right? So that's basically what we are going to predict. So when we only have the qxt brought to the xt minus 1, like when we only have like this information, how we can get basically this reverse the transition is basically the things that we are going to learn using the kind of the neural net the training. But the thing is that while we don't know how exactly we can get this, this is something that we cannot basically directly derive from all the formulation. The thing is that if we consider this, which is like conditioning not only by the xt, but also x0 as well. If we basically see this kind of specific the case, that like we're having some kind of the condition of the probability density function, the conditioned by both the xt and the x0, then now we can derive some kind of the analytic form of this. So this is like one thing that we are going to see. So this derivation might be a little bit like dirty, but also the good thing is that the closed form of like this, conditioned by the both xt and the x0, is also defined as another the Gaussian distribution, like this. But at this time, the mean and the variance is a little bit like dirty. As you can see that the mean is defined in this form, and the variance is defined as like this form. So the alpha t and the alpha t hat is coming from the previous slide. So we are now defining this as kind of the Gaussian distribution, which mean and the variance is defined in this way. So the question might be is that how we can exactly derive this. So we are not getting into all the details for that, but basically this is something actually you can do yourself. This is actually quite doable. This is just coming from the base rule. So we can rewrite this posterior distribution in this kind of form from the base rule. Then what we can see is that actually this part is basically the full transition because the xt minus 1 is already conditioned based on the x0, right? So you can see that this is basically the transition that we know, which is kind of simple. And the other two terms, basically some kind of the distribution from the condition by the x0 is something that we have seen in the previous slide. So now we can see like basically how we can calculate the Gaussian distribution for these two cases, right? Then now what we can see is that basically this is like another kind of the combination of like three Gaussian distribution, right? So by combining the three Gaussian, so basically this is Gaussian, this blue one is the Gaussian, and the other two are also the Gaussian as well. So based on the combination of like these the Gaussian distributions, we can now define this specific form as another the Gaussian distribution. So if you basically write down all the things, then you can see that at the end of like all the derivation, we're gonna see that the posterior distribution will basically have this form of the Gaussian distribution, which is having this mean and this variance. Makes sense? Okay. Yeah. So here all the key thing is that you don't need to remember like all the equation. Just the key thing is that now the mean is defined as kind of the function, which is defined based on both the xt and the x0. So the mean is basically determined based on the given the xt and the x0, right? The thing is that the variance, the covariance is basically defined as kind of some the values that we are defining, right? So we have seen that the beta t is some kind of the usual parameter. Alpha t is nothing but basically 1 minus the beta t, right? And alpha t hat also defines kind of some product of the alpha t, right? So these are basically some all the values that we are defining. So now the covariance, the sigma term here is defined as kind of the from the based on the usual defined parameters. So which is basically not the basically value, which is basically determined based on the condition of the xt and the x0, which is kind of fixed value for the arbitrary the time step t. For each of the time step t, we can directly compute the covariance term. So the thing is that we just need to know the mean, and the mean is basically determined by both the xt and the x0. So this is also the key things. It is clear. And then actually what we are going to see is that what we can see that actually each of the xt is sample of like this Gaussian distribution. So this is basically the formulation that we have seen as kind of the jump from the x0 to the xt, right? So each of the xt can be basically written in this way because it's one of the sample of like this specific the Gaussian distribution. And we did some kind of the sample of the unique Gaussian epsilon t, which means that we can, if we have the xt and the epsilon t, which is defining the the xt from the x0. So we basically we can see that the x0 and the xt have this kind of the relationship with this formulation with some kind of a sample from the unique Gaussian, right? Which means that if we know the unique Gaussian, the noise epsilon t, which is basically resulting the xt as kind of sample at the time step t from the x0, then what we can do is that now we can rewrite the x0 as kind of some kind of the formulation defined based on the xt and the epsilon t like this. So now we can see that each of the x0 can be rewritten basically with some kind of the xt and the epsilon t, which basically resulting in the xt from the sample from the x0. So now what we can see is that we can also rewrite the mean or like this the posterior distribution as kind of some formulation defined with the xt and the epsilon t. So basically this epsilon t is basically the unique Gaussian the noise, which basically makes the xt from the x0, right? So basically you can say that if we know the xt and also the epsilon t as well, then this epsilon t is basically encoding the information of the x0, right? So we are just like simply replacing the x0 with some kind of the formulation, kind of the xt and the epsilon t. So that's basically what we are going to do. Clear? Any questions on this? So that's basically things for the this posterior distribution, and why we are basically seeing this specific the distribution. The thing is that while basically we are optimizing this specific loss function, after basically long the derivation, what we can see is that actually like minimizing this loss function becomes the same as kind of like minimizing this specific loss function. This is kind of like very long derivation, so you can check out some of the papers, like how exactly we get this. But from this, basically what we can see is that minimizing the original loss function becomes the same as kind of like we are matching the reverse transition to be the same as kind of like this specific transition. So this was basically the transition that not transition, the distribution that we have seen in the previous slide. And what we can see is that if we just try to match the learned the reverse transition to be the same with this specific probability the distribution, then that's basically minimizing this specific loss function. Which means that now what we are going to do is that we are going to, and we know that this is another the Gaussian distribution, right? Actually, we want to model this as kind of the Gaussian distribution. So the thing is that let's basically learn the trained neural network in a way that we match this to be the same with this. And what we know is that from this the distribution, we know the mean and the covariance. Especially the covariance is basically is some kind of known parameters. For the arbitrary time step t, we can directly compute the covariance, right? Which means that if we can basically get the information of the mean of this specific distribution, then that's basically what we need to know to basically match this to be the same with this distribution. So here, basically the point is that given the time step the xt, basically how we can basically get this information like this reverse transition in a way that the mean becomes basically this mean. Any questions on this? What does the epsilon q, what is that? The question is this expected value. So basically we are basically getting the expected value for all the samples x0. X0 is basically the data point. So we are having some kind of the data samples from the data distribution, right? For all the samples from the x0, we are basically taking the expected value for this quantity. So specifically, this will be the case that we are basically computing basically, yeah, for all the samples that we are having coming from the x0, like we are basically taking the sum of this. Yeah, for the samples of the data distribution that we have, we are basically summing up all this kind of quantity and minimizing this. And why do we minimize this? Because like actually it's the same that here we are having the minus. So it's the same as we are maximizing the log probability. So we want to maximize the probability for each of the data sample once we basically get the learn the data distribution p theta here. Right? And this can be rewritten as like this form. Also expected value for the arbitrary time step t, and also the samples of the x0 and the xt. So we want to basically maximize this. And this becomes basically the case that we are basically matching this to be the same with this distribution. And we know that this q xt minus 1 conditioned by the xt and the x0, this is like Gaussian distribution, and we have seen like how we can derive the mean and the covariance. And the thing is that the covariance can be directly computed from the parameters that we define. We just need to get the information of the mean. And also what we have seen in the previous slide is that the mean is now defined with the xt and the epsilon t, which basically resulting this xt from the sum of the x0 information, right? So given the xt, how we can get the Gaussian distribution of this with some kind of the mean of this Gaussian. So we have the xt, and the only information that we need to have is basically epsilon t. So given the each of the xt, if we can somehow predict the epsilon t, which resulted this xt from the sample from the x0, then we can directly compute this mean information, right? So it turns out that like all the kind of some sort of convoluted, some kind of the derivation, what we need to see, what you can see is that the only information that we need is actually just like epsilon t here. So what we are going to do is that, like, given some kind of the the xt and also the time step t, we basically get the information like, sorry, let me just go back. So basically we want to get the information like xt x0, right? And even we just need to have the mean information, because then we can directly compute the covariance as well. So how we can calculate the mean? Obviously, we can, from the xt, we can predict the x0 that results in basically xt, like, where basically xt came from the which basically x0. Or the other way around is that instead of like getting the x0, actually we can just get the epsilon t, which basically resulting in basically the xt from the x0. So if we can basically, given the xt and the time step t, if we can predict the epsilon t that results in basically the xt, then we can compute the mean. Then this is basically defining the reversible process, xt minus 1 minus xt. So this becomes the mean over basically this reversible process. So that's basically what we are going to do. So what we just need to learn using the neural network is that arbitrarily given the random the xt and the time step t, we are basically predicting the epsilon t. I mean, actually, the other option is that we can consider like predicting the x0 instead of the epsilon t. The practical reason that why we are basically predicting the epsilon t instead of the x0 is that if we know that epsilon t is basically samples of the unit Gaussian. So all the numbers, the scales of this kind of the data are basically well normalized, basically some numbers in some kind of 0 to 1 range. So it becomes much easier to train the neural network. So in the neural net training, basically normalizing the data set and categorizing the data set is the most important part. So if you basically train some kind of the network using the ImageNet, you basically do some kind of the scaling or some centering of all the image data, doing some kind of the data normalization. This is basically a very crucial part in terms of like training the neural network. And what we can see is that in our case, in this specific case, all the data are basically naturally normalized in terms of that all the numbers that we are going to predict becomes the samples from the unit Gaussian. So that's really kind of good thing. So basically, it turns out that what we just need to predict using the neural net is like basically given the arbitrary the xt and the time step t, from the given this information, we are basically predicting the epsilon that basically gave the xt from the x0. So that's basically what we are going to do. Oh, sorry. Any questions on this? Is this clear? So in the neural net training, what we are basically going to do is that given the x0, given the x0, we are basically sampling the epsilon t in a way that we can basically jump from the x0 to the xt. Right? So this becomes basically xt, right? So from the arbitrary the x0, we can sample the xt basically by sampling the epsilon t and computing this. And this becomes the xt, right? Then basically using the neural net, we are basically predicting, doing some kind of reverse weight. Now, given the xt and the time step t, we want to predict the epsilon t that resulted the xt from the x0, right? So this is basically what we are going to do. So we are going to train the neural net in a way that we are basically minimizing this. So obviously there's some kind of some complication derivation in a way that there are some kind of the weight for each of the time step t. But in some practical cases, like people just ignore this kind of the weight, and even without like having this weight, actually just minimizing this loss function actually works quite well. Some practical reasons. So that's basically what we're going to do. So in summary, in the training time, what we are going to do. So as I said, in the training time, we don't need to do some kind of some sequential process. We can directly jump from the x0 to the arbitrary time step t. So in the training time, what we are going to do is that for any kind of the x0, which is like one of the sample that we have, we are also sampling the time step t here, any kind of time step t here. And then based on that, we are sampling the unique Gaussian denoise. And then we compute the xt, which is basically jump from the x0 to the xt by just adding the small the Gaussian denoise. And then what we are going to do is that we are going to train our the neural net in a way that the epsilon, which is predicted by the neural net, given the xt and the time step t, becomes minimized, the same with some kind of the noise that we sampled. So that's basically some kind of things that we are going to do in the training time. Make sense? So actually implementing this is the part of the assignment 3. So you will need to basically see exactly how this kind of the procedure basically works. And actually at the end of the day, you will gonna realize that actually while all this kind of process looks a little bit complicated, actually implementation wise, you'll see that actually the implementation is quite simple. It's basically not just a few number of the lines. And also you see that actually this training and also this generation step works quite well. So that's basically also very interesting part. Can you solely reverse the study question from the pre-selection? Yeah. So basically, you can check out the DDPMD paper, and also I guess I can also provide some more kind of the reference kind of the documents that you can check out some of the details in the formulation. Any other questions? And also for the generation time should be done in the more the sequential way, right? So any kind of the capital T, which is the sample from the unique Gaussian, now we are going into the reverse process in a way that now we are predicting the epsilon T because we don't know this information, right? So by running the propagation using the neural network, we get this information, and then we basically compute the x0, getting the prediction of the x0 based on the xt and the epsilon T, compute the mean of the distribution. And then basically, based on the mean and the some sampled another kind of the noise, we are getting back to the xt minus 1. So this is coming from the this distribution, right? Xt minus 1, xt and x0, right? From this distribution, basically we are computing the mean from the neural net prediction, and then sampling the unique Gaussian denoise in a way that basically having this sample of like this distribution, and then getting the xt minus 1. And then we can repeat this process, right? Is this clear? Then here, one quick question might be is that like, so in the fold process, we have seen that we can jump from the x0 to the any arbitrary time step time t, right? Then can you also do this kind of a jump from the x capital T to the arbitrary time step t in the reverse process as well? Do we really need to do this kind of some kind of the iterative process in the reverse process as well, or can't we just like directly jump from the x capital T to the arbitrary time step? This is the question. Yes, really? I mean, yeah. There are also some people who know some kind of the next kind of things that we're gonna discuss. But basically, the thing is that in the reverse process, we can directly jump from the x time capital the time step capital T from the arbitrary time step T, because as you can see, we are predicting the mean of each of the one step the transition from the neural net prediction. And basically, the mean is basically predicted based on the xt and the time step t. So once we basically get this information, we can predict the mean, and then we can do some kind of get some the information of the Gaussian distribution for each of the transition, right? So basically, to calculate the Gaussian distribution for each of the single step, we need to get the data point from the previous step. So basically, here the Gaussian distribution. In the fold process, all the transition, the single step transition was basically given. that was basically usually define some kind of the transition, right? But here, basically, all the single-step transition is basically predicted using the neural network, and that also requires the data point in the previous time step. So that's why we cannot directly basically jump from the x capital D time step t to the any arbitrary t time step. We need to have some kind of the intermediate data point in a way that we can predict this mean value for the single-step transition. So that's why we still need to have some kind of some iterative process in the recursive process. But obviously there are some kind of some tricks in terms of like how we can still some kind of like skip some of the intermediate steps and boosting this kind of some sequence of the process in the generation there as well. So that's basically what we are going to also discuss next time. Is this clear? So yeah, we are having this kind of the training step, like for any kind of given the sample the data point, sampling the time step, sampling the Gaussian denoise, computing the xt, which becomes the sample from the xg to the time step t, and then basically minimizing this loss function in a way that the neural net can basically predict this epsilon, right? In the sampling the time, now we are sampling from the x capital T, which is also the Gaussian denoise, this sample, and then basically we are computing, predicting the epsilon, computing the mean of the basically the reverse the transition, the Gaussian distribution, and basically by adding this Gaussian denoise again as well, then we are getting the xt minus 1 and repeating this process. So this is our the training step and also the inference step. Any questions on this? Yeah, I guess your brain might be basically spinning around with some kind of some lots of the formulation for today. So I have a few more slides that we need to actually discuss, but I guess we can stop here. We can basically end 5 minutes earlier so that you can also have some time to basically digest some of the formulations here. And let's also continue discussing like how this kind of the diffusion model, the idea is kind of like related to the VAE and also the other core models as well, and how we can also boost up the process of the reversibility process, and also how we can utilize this kind of the generated models, not only for the generation, but also for some editing process as well. And at the end of all this kind of discussion, we can also see how we can apply this idea for the 3D generation, and also even how we can utilize the image generated models for some kind of the 3D generation, even without having any kind of 3D priors as well. So that's also what we are going to discuss next week. And if you have any questions on this, please feel free to post the questions on this. So let's stop here and let's continue next Monday. Okay, bye.